Thank you, Masha. So I will come back to the topic of signaling that ISAM introduced. And our work there is focused on trying to deal with the complexity of these networks so we can actually make network reconstruction scalable to whole organisms, or at least whole cells. As Roman told you, this is a challenging task already at the metabolic network. But still we had metabolic wall charts of basically global metabolic reconstructions available for decades. So the methodology is there. We have reasonably well-established formalism for metabolic network reconstruction. It is due to the fact that metabolic networks are largely defined by their topology. So components being present are typically enough for them to actually be available for the outgoing reactions. We also have nice features with mass transfer, right? So we have a pretty clear relationship that everything that goes into the network must come out somewhere. If we go to signaling, nothing of this holds true anymore. So components being present are no longer sufficient for predicting their activity. Instead, we need to account for the specific states that these components can be in. So we have signaling components that are there all the time, and just under certain circumstances or after certain modifications do they become competent for signaling. In addition, we have information transfer. That means there is very little conservation we can use. There is no clear relationship between input and output. And we simply need different strategies to deal with signal transduction networks. And there are particular two problems here that I will introduce now, and that's the combinatorics of the networks, but also the fact that these different states does not always correspond to what we can actually measure. So to the left here I have a small toy example of a signaling network. So it's 4 protein kinases in a sequential cascade, phosphorylation cascade ending up on a transcription factor, phosphorylation events indicated by red arrows here. It's a pretty compact display. It's easy to read this as information transfer. I mean, directed edges. Obviously, these are activating. But this is actually not what the graph says. It just tells us that these are the possible events in the network, and it gives you no information on the causality. In this particular case, they are activating phosphorylation, but that's not captured in a topological network diagram. So something is missing here. And in signaling, the classical approach to get this network actually equivalent to these metabolic maps that actually nodes mean I'm here, I can undergo the reaction I'm connected to, is to expand the description from a single node per component to a single node per state. So we enumerate all possible states in the network. And this is pretty intuitive. It's also very visual. It's easy to understand. It is for small network, but unfortunately the network complexity increases very, very rapidly. This is the combinatorial complexity, and as you see, the corresponding diagram for even this small network is displayed to the right, and is pretty complex already, and pretty difficult to read. A more subtle problem, which is related, but not as obvious, is the fact that many of these combinations or modifications that we now enumerate has not been directly measured. We don't typically in the lab measure anything more than single or perhaps double phosphorylations at a time, single protein-protein interactions. And we try to project this rather low resolution information on a very highly specified model. We introduce ambiguity and simply obfuscates the interpretation of the data. So we actually trying to model or describe or visualize something we actually don't even know if it exists in nature. We don't have this problem for a topological network because these edges corresponds to a general decontextualized reaction. So we know these phosphorylations may occur, but we haven't specified the context of them, which means that this is actually in accordance with the experimental measurements. So perhaps both from a perspective of compactness or an adherence to empirical data, perhaps a topological visualization is a step closer than the specific state description, given that we can also add the missing causal information to this. And the way we do that is simply by adding yet another information layer. So the same network, again, to the left here, I've transposed into a bipartite graph to the right. And each edge in the left diagram is a reaction. This reaction is now represented by a red node to the right. And this can be two proteins interacting, or one kinase phosphorylating a target, for example. And from each such reaction node, there is an outgoing edge that towards the state that's actually the result of this reaction. So for a protein-protein interaction, of course, it's a dimer. For a phosphorylation event, it's a phosphorylated species with a specific phosphorylation sites. And as you notice, this results in a couple of node pairs that are dissociated or disconnected from each other. And that exactly captures the lack of information transfer we have in a topological network. So in order to connect them together, we need a second information layer, as I said, the continuances or contextual constraints, which tells or keeps the information on how these different states are regulating downstream reactions. So in this particular case, if you look at the last reaction, it's a MAP kinase phosphorylating its target. And of course, we know that this only happens when the MAP kinase itself is phosphorylated on two residues in its activation loop. And this is then represented by these incoming edges here. And I should point out here that these states are distinct from the states in the specific state description I mentioned before. These are not by themselves mutually exclusive. So it corresponds to the entire set of molecules that share a certain property, for example, a specific phosphorylation. And to get a more highly defined state, we simply need to take intersection of two or more such states. Another feature that's worth noticing is that if we go to this description, we can see a pretty clear information transfer. We have unidirectional edges, reasonably easy to lay them out in a hierarchical manner, which is not the case when we have this specific state description, where the sheer number of states and reactions actually obfuscates the information transfer in the system. So our take on this is not primarily graphical. We work in a text-based definition format, and we can use this then for generating all these visualizations. But I'll still introduce it because it might be the easiest to see the data, what the information is. So we have reactions are defined in the most simple format by basically like high throughput data, right? We have two proteins that has a relationship, phosphorylation or a protein-protein interaction. And that's the possibilities of the network. So this is the decontextualized reaction. We have said this can happen. We haven't said anything about when this is true, when this reaction actually may occur. On the other hand, we have the contingency information, which provides all the contextual constraints on these reactions. It tells us that our protein kinase is only active after it's already been phosphorylated and activated. And this is a similar simple structure. It's a pairwise relationship between reactions and states. And by keeping these two information contents separate, we can avoid the problem with the combinatorial complexity that I mentioned, but also we can keep the description at the same granularity as experimental data. And of course, we are not the only one working with this. As Roman introduced the systems biology graphical notation, they have a formalist there called entity relationship diagrams, or ERs, which use a similar distinction between reaction information, which is the possibilities, and the contextual contingency information. And so we developed this formalist. We implemented a software tool to use this for visualization and model generation. And we set out to map the MAP kinase network in yeast. And compared to the metabolic networks, this looks like a rather simple system. We have roughly 80 components, 80 proteins. We have about 180 distinct states that appear here, or elemental states, which is single specific phosphorylations or protein-protein dimerizations. We have slightly more than 200 reactions because some of these states are generated or destroyed by different enzymes, phosphatase kinase acting on the same phosphorylation. But we have no clue how many specific states it would would come to. We know that a small fraction of this network, say 18 components or so, would require about 200,000 specific states, which would already blow it out of proportion with the metabolic networks. But the visualization here is a simple topological network. We have added around the central nodes domain information, residue information when we know the exact phosphorylation sites. We can of course look at this for the whole network, which again then on topological level is rather trivial. However, I should say that if we would go back to the global protein-protein interaction measurements, these three pathways would be confounded by a lot of cross PPIs that would appear to confuse the pathway layout. As I said, we can also look at this in the informational, with the informational layer. This is the same bipartite graph that I introduced before. Red nodes, reactions, they produce and consume states. They are represented by blue nodes, which can activate or inhibit reactions further downstream. And as I said, if we needed more highly defined states, we simply take the intersection of three states to give the regulatory modification that's needed for a reaction to happen. And if we do this for the pathways, they actually fall out very nicely into pretty linear pathways. So we have to the left here the cell wall integrity pathway, to the right the high osmolarity glycerol pathway, in the middle the mating pathway, and the only exception to this pathway distinction is the module here involved in cell polarity that plays in two pathways. Of course, this is not really an easy to read graph on a single slide, but I must remind you that this is 400 nodes, and it's basically the complete regulatory information we have about a MAP kinase network. And if we would do this in a specific state description, 100,000 states would not be sufficient. Okay, so this is basically what we are doing on visualization, but I would like to continue this one step further and talk a little bit on how we could go on and actually also analyze these networks computationally. So if we can capture a regulatory structure of a signaling network in just a few hundred nodes, can we also simulate it in the same way? And to do this, we wanted to have something that can handle large networks. We wanted something that keeps this context-specific activation because we had shared components playing in more than one pathway. And of course, we would like to do this automatically. We don't want to spend any extra energy on model generation, and we don't want to parameterize these models or experience as combinatorics. So what we settled for was a Boolean formalism, which used the same reaction state distinction, where we have reactions that generate or destroy states, and states that then via continuances defines which reactions are active. Okay, so we did this for the MAP kinase network, and we used this in an iterative way to actually find things in these pathways that were missing or features that were missing to actually reproduce the expected behavior. For the interest of time, I'll not take you through the big example, but as a toy example of the pathway to illustrate the method in relationship to the classical Boolean. So to the left here we have a topological Boolean network. So we have just the components as active or inactive entities. We have two different signals coming in. Each of these signals would activate the shared component in the middle, which would promptly activate both outputs, meaning that we could have no signal specificity in such a model. And accordingly, we also see that regardless of the initial stimuli, we have almost everything on, or both outputs are on. In the other version, we have a state-oriented approach to the Boolean. We can see that the different input activate different states of the shared component, which then maintain signal specificity. And we see, depending on the input, we get different sets of outputs. So at least it fulfills the criteria of context-specific activation. It's also something we can generate automatically, and we don't need to parameterize it at all. So just to show you a snapshot from the software, this is another small example of a cyclic or oscillatory model. We see states lighting up or when they're on, fading out when they're off. And to the right we see a state space trajectory. And here we see the orange dot, we're stuck in a cyclic attractor. We can use this for rather crude model validation then. So the idea here is not to have a dynamic predictive model of a cell, of course. We cannot do that reasonably with Boolean modeling, but we can see, is this structure, is the network information we put into the database sufficient and able to at least predict the qualitative behavior we expect from the network. Okay, so to summarize this, I hope, or the main point here is that we need a different approach to, or some new approaches to make signal transduction networks scalable. So what I mentioned in the beginning is we have the topological networks. We can manage visualization on a topological level, but topological networks themselves are not sufficient to capture the functionality of a signal transduction pathway. On the other hand, we have the specific state descriptions, which enumerate all possible states of the network. This is the intuitive extension, taking topological network, adapting it to signal transduction. Unfortunately, this leads to a very high complexity, and despite this, this is still the most, or the preferred method of network reconstruction. It's used by both large literature mappings, it's used by Reactome, etc., the protein interaction database, or pathway interaction database. But it doesn't scale very well, and it forces reductions. It forces omissions, selective representation, which basically means that you take this very hard work, because manual curation of networks is really hard work. You take this good work and you mix it with equal parts, or even sometimes a larger part of arbitrary model or network reduction. This is a pity, because it's information dilution. We believe that the reaction continuity separation allows us to deal with this. It's a way that enables us to complement a topological layer with an informational layer to actually manage these networks without generating complexity and also without straying from actually the experimental basis of the data. And as I said, we are not the only one working with it. We have the ER format of SPGN that was introduced before, or at least SPDN. But the underlying database should probably be used as separation. What I've showed you more is that we have a text-based format for this, which has some advantages over purely visual formats, not the least in keeping track of references, etc., which is something I did not talk about. But we can use this for automatic visualization, automatic model generation, not only of the formats that or these graphs or models that I showed you, but we can also support the SPDN formats, for example. We can export rule gradient-based models. So the underlying data structure is compatible with very many different methods of analysis. And what I mentioned here was just the Boolean modeling that can be used iteratively for crude model validation with rather low cost, until you come to the point where you're really confident enough that it's time to build a dynamic model of the system. Okay, that's basically it. I'd just like to point out that we have a software that's open source, freely available. And before I end and return the word to Masha, I would like to thank the people who helped me do this work, our funding agencies, and you for your attention. Thank you.
Go ahead.
Hi, Marcus. Thanks for this presentation that carefully laid out the problems of signaling. So the last part, it's consistent SBG and AF logical modeling. When you mention this is a graphical representation of actually a type of modeling that is pretty well developed called rule-based modeling with languages like BioNetGen or Kappa. Did you consider using that at the top layer to represent?
So the rule-based modeling is very closely related to this. So it's easy for us to translate this to a rule-based model. But the rule base is somewhere in between. So a typical rule consists of one, what we call an elemental reaction, so one reaction event with certain reaction context. And sometimes this is a single requirement, and then it's basically identical with what we do. But sometimes this is already a compound of a number of states that need to be true or false. So it's very similar, but there's one further step back where we split this apart in each and every such constraint is enumerated separately and also referenced separately, which makes it easier to actually provide the literature evidence for it.
No, I entirely agree. Rule-based modeling is on the top, but then once you define your rule, you generate your either logical model or OD-based model.
Yeah, no.
Eliminating the necessary information.
No, you're right, but already rule-based modeling is one step further because some of the rules is integration of, it's only one reaction, but sometimes more than one of these continuances, we call it. So it's already a concatenation of related information. But yes, it's very closely related.
We have time for another question. In fact, maybe I can ask you just a fast question. You mentioned that you were speaking in the end about model validation, and so you didn't really have time to go into detail, but I was wondering if you recommend certain procedures for that before moving towards more dynamical modeling, or is it just for the user to kind of decide when he's satisfied?
So I think that before the model or the network does not even work on a qualitative level, there's no reason to invest any energy in building a dynamic model, which is much more costly, both for computation analysis and also work with parameterization, etc. So what this is a pretty straightforward and pretty simple, actually, tool for just seeing, can the network, as we defined it, do the signal go from the input to the output, or does it get stuck somewhere in the middle? And of course, if it gets stuck, then no parameter set will help you get it through.
Okay. Thank you. So thank you all for participating in